Class of physics. In previous video, we have studied the law of conservation of linear momentum in case of variable masses, that is taking an example of single stage rocket. So the key feature is the initial momentum and the final momentum of the rocket remains constant. That means even though the mass of the rocket decreases because of the fuel is burning, then to balance that momentum, to maintain a constant momentum, the velocity of the rocket increases. Okay. Now using that theory, we are going to derive an expression for the velocity of the rocket at any instant of time. So let's derive that equation. Conservation of linear momentum in case of variable masses, that is single stage rocket. Okay. So this derivation is very important. Okay. So consider a rocket initially moving with velocity v and having the mass m plus dm. Now here I am not going to consider the mass of the rocket as m, I am going to consider the mass of the rocket is m plus dm, because to burn the fuel I am going to remove this dm amount of the fuel. Okay. Then the remaining is m. So here there is a rocket. Okay. This rocket having mass m plus delta m at something in space at a time, and it has velocity v. The rocket engine burns rocket fuel which leaves with an exhaust speed of v. That means when it starts burning, the fuel is exhausted, that exhaust gas, it has velocity v. Okay. So here, so the gas is exhausting, so this has the velocity v. During a short amount of time dt, the rocket engine burns an amount of fuel dm. Okay. So in a time interval dt, the amount of fuel is burning, that is equal to dm. Okay. So dm amount of fuel is burned out in time interval dt. So then in remaining steps we are going to consider the sign of the dm. So that is important because some concern and the confusions. Okay. The initial momentum of the rocket and the fuel is, so here the conservation of momentum, that is initial and the final, remains constant. For that we have to write the initial momentum of the rocket and the final momentum of the rocket. The initial momentum of the rocket includes both the whole mass of the rocket, that is includes with the total fuel. The mass of the rocket now it is m plus delta m, okay, or dm, and it has velocity v. The product of mass and velocity will give momentum. For that the initial momentum is m plus delta m into v, or dm is dm into v. Okay. Expand this one, then m into v and dm into v. So that p initial is what? It is mv plus, here mod we are taking because of the sign conventions, dm into v. After the amount of fuel dm, is burned, the rocket increases its velocity to v plus dv and its mass decreases to m. So the total mass is m plus dm. In that, dm amount of the fuel is burned out. For that the remaining mass is only m. So when mass decreases, to maintain a constant momentum, the another quantity should be increases. The another quantity is here, it is velocity. For that the velocity increases to v plus dv. Then the mass is m. So the final momentum of the rocket and the fuel is, now I am going to write an equation for the final momentum of the rocket and the fuel. So v final equal to m into v plus dv plus dm into v minus v. Okay. So here some complication is there. The remaining mass is what? It is m. The remaining mass is m, and the velocity when it has mass m is v plus dv. So this is the mass of the rocket, and this one dm into v minus ve. So this is the final momentum of the fuel. Okay. Final momentum of the fuel. So dm amount of the amount of the fuel is burned out, and it has velocity v minus ve. So this v minus v is exhaust velocity, and v is the velocity of the rocket. Now expand this one, then mv and m into dv. So then plus dm into v and minus of dm into v. So we expect the total movement of the system remains constant. Okay. So the condition is the total movement of the system is remains constant. For that, before is equal to after, or after equal to before. Here the condition is final momentum equal to initial momentum. So these two momentums we have to equate. Okay. So these two equations we have to equate. Which one? P initial and P final. So that P final is what? It is mv plus m into dv plus dm into v minus dm into v is equal to, and the initial momentum is, here it is. Okay. From here it is mv plus dm into v. Then mv plus mdv plus dm into v minus dmv equal to mv plus dm into v. That same step is written again. Here the cancellation terms which are cancels. So here mv is there, and in right hand side also mv is there. These two get cancels. And then in left hand side plus dm into v is there, and in right hand side also dm into v is there. For that, these are written in the same colors. Okay. So this purple get cancelled, and these two are in green colors, so these two get cancelled. The remaining is m dv minus of dm into v, so that is equal to 0. Okay. So the remaining is m dv minus of dm into v equal to 0. The mass is decreasing, so the change in mass dm is intrinsically negative. Okay, that is dm is less than taking as 0. So that this mod of dm value now we are taking negative. For that, this whole becomes plus of dm into v. Okay, this sign convention is important. Please remember this one. M dv plus dm into v equal to 0. Next, take this dm into v into another side, then it becomes m dv equal to minus of v into dm. Again, this will take negative sign, and dv equal to minus of v into dm by m. Now we need to integrate this equations. So negative here, v, sorry, negative, it is v, exhaust velocity, v, the exhaust speed is constant. Okay. The mass decreases and the velocity of the rocket increases, but here the condition is the exhaust gas having the constant velocity, that is v is constant. Now integrate these equations. So when you integrate, then okay, now again I am rewriting that equation, dv equal to minus of v into dm by m. Now we have to integrate these equations. Now here the ve is constant. What is ve? Ve is exhaust gas velocity, that is constant. For that, we have to integrate only. Here it is velocity dv is equal to minus of v into integral of dm by m. Here we are going to integrate this 1 by m because the mass is varying, mass is decreases. For that, we have to integrate that mass term. Here the limits I am taking v initial to v final, that is initial velocity to final velocity, and initial mass to final mass. Okay, mi to mm. So when you integrate this one, here this integration term becomes v, integration of dv is v, the limits are v initial to v final equal to minus of negative sign, minus of v. Okay, this is as it is because the velocity of exhaust gas is constant, and this integration term becomes ln m. Okay, so that is natural logarithm, so that is log m. The limits are initial to final. So substitute these limits, then it becomes, when you substitute these two upper and lower limits, then Pf minus Pi is equal to P is as it is. When you substitute these mass limits, then it becomes log of Mf minus log of Mi. Okay, that is final mass and initial mass. phi f minus phi equal to pe. Okay. Just I'm going to take this negative sign into the bracket, then it becomes ln mi minus ln or log mf. Then phi f. Okay. Now our aim is to find the velocity of the rocket at any instant, that we taking it as final velocity of the rocket. So phi f equal to, take this minus of v into right hand side, then it becomes plus phi. So that phi plus p log mf by mi. Okay. So this is the final expression. It is velocity of the rocket, Pf equal to Pi plus P log mf by mi by mm. Here mi is greater than mf, that is, this is the case, the initial mass is always greater than final mass of the rocket. Okay. Natural log will be positive, this natural log will be positive because mi is always greater than mm. Of course we would expect that since we also expect qf is greater than pi. Okay. So this is the conditions, the final velocity of the rocket is greater than initial velocity. See here, initial mass of the rocket is greater than final mass and the velocity is opposite. The initial velocity is less than final velocity, so mass decreases, velocity increases, hence the momentum will be balanced, that is constant. The final expression Vf equal to Vi plus V log mf by mi by mf. Okay. So this is important derivations, please practice this one, and expression is also important. Okay. So for this, law of conservation of linear momentum is complete. In next we are going to briefly study multi-stage rockets. So this is expression for single stage rocket. In next class we are going to see what is multi-stage rocket and what is the purpose of using these multi-stage rocket, that is advantages of multi-stage rockets. Thank you.